He said last time this didn't respond, it was because it wasn't plugged into the computer. He was doing so good. It was because I moved the computer. Probably going to be stuck going out front. All right, so anyway, what we'll do is we'll kind of look at on page 57, the definition that says there, an index set of vectors is said to be linearly independent if the homogeneous setup has only the trivial solution. Otherwise, it's linearly dependent. You know, the idea of dependence and independence is that if you think about straight lines, if in a plane, a line lays on top of itself, you know, like if you have y is equal to 2x plus 3, and then you go y is equal to 4x plus 6. It's just a multiple of it. It's the same line, except it's just a multiple of it. So the line lays right on top of itself, and those are dependent. Independent means that they're not the same line. They're independent of each other. So that's what this is, because it's just, we're talking about writing, rather than equations, writing it in terms of matrices. So taking equations and writing it in terms of matrices. So on 58, on the next page, it's saying the columns of the matrix A are linearly independent if and only if the equation AX equals 0 has only the trivial solution. So the homogeneous set of equations that has only if there are no free variables, you're going to have an independent set of equations. Theorem 7 there says an index set of vectors, of two or more vectors, is linearly dependent if and only if at least one of the vectors is a scalar combination of the others. So if you could take one of the vectors and multiply other vectors together and get that vector, then they're dependent. show you some examples. Theorem 8 says if a set contains more vectors than there are entries in each vector, then the set is linearly dependent. So if you look at the A matrix, you can see that the number of columns exceeds the number of rows, and you know that if you try to do echelon or reduced echelon, you will have free variables, and that will give you non-trivial solutions. And if there's a zero vector, so let's see. So I wish that would work. Okay, the first set of problems are in 61. Determine if the vectors are linearly independent. So for that number 2, what we can do with that is we can just see whether we in echelon movement, if we have ones down there. So I'm just going to put this in. This form. So the easiest thing to do with this thing is just change it around, bottom or top. And now you notice that when we have the turning points on each one of those. So that's going to have the homogeneous set of equations. This would have only the trivial solution. And so the question is it linearly independent? The answer is yes. It's linearly independent. If you look at number 3, where you have 1, 3, and 1, 3, 9. This vector right here is just a scalar multiple. So it's not independent because the vectors, one vector is a multiple of the other.
Which means it's not independent.
What's that?
Which means it's independent or not independent.
It's a dependent set. Did I say independent? Did I say independent?
I don't think
Okay. Well, it's dependent. The first one is independent. Then it says, determine if the columns of the matrix form are linearly independent, justify the answers. So this is, we'll just use that same. And we'll just take a matrix. Now you can see the number of columns is greater than the number of rows, so it could be independent, dependent. And so theorem 8 don't apply, so we're back to trying to put this in some sort of echelon form. What do you want to do first?
Trade. There's 3 along.
Okay, so take this one up here, so we get one in this position. Leave this one right where it's at. What's that?
For what is now the first row should be the last entry be a 3, not a 0.
Was this a 3?
Yeah.
I'm good. So then I just have to get this one switched out. That was 4. Slow. So I'm multiplying by minus by 4. So it's 12. I'm multiplying by minus 1. It's negative 15, so it's negative 9. And then we can multiply this one by minus 3. So it's 0. This is 0. And then multiply this by 4. 16. 7. Now I can switch these two around. So I would have an independent set of equations. Because what has to have is if you're multiplying this out, what you have to have is x1, x2, and x3. Because when you're multiplying matrix multiplication, it's this row comes that high. So having that 4th row only says that you have another equation. So you have 3 independent equations. Now 8 see, this whole problem, if you were trying to solve it, you would have to have x1, x2, x3, and x4. Because that's the only way you can multiply this out. That says that what you have is you lack a fourth equation to be independent. So you're going to have a free variable on x4. The number of columns, p, and the rows, like, to be consistent. Theorem 8. And so p is 4, and n is 3. And that says that it cannot be, it has to be inside. Because you don't have enough rows to get 4 independent equations. So it's, and that's theorem 8. And it says, in the next exercises, for what values of h in B is B3 in the space in the span of B1 and B2? And we're going to have to just evaluate how many those vectors put in the matrix. But the way we're treating this is going to be an augmented matrix, because what we're treating this as is AX equals B3. So in this particular case, this becomes the augmentation of this matrix right here. And what we'll do is we'll just check and see whether we need to get turning points on these two places. And then see what H is. So I'll just leave that first one. And then I'm going to multiply by 5. That's 0. You can see there's no way that we can get turning points down this. So B3 is not in the space of B1, in the span of B1 and 2. So that's Well, you keep that one. The next thing is saying, it's asking you, B, for what values of H is E1, B2, B3 linearly dependent? So technically you're asking this. Ax equals 0, do that ordinary matrix there, where B1, B2, B3 are in this A, and then you actually have 0 up there. So you just do log matrix. And this is, that's what's being used. And then if you try and solve this, you're going to have the same problem as you had before. I mean, you're going to get, you basically have this, you're going to get this, but it's just going to be a set of zeros. And you question to ask for what values of H is linearly deep. Well, there's no values of H. You can't get a 0 in there. So, and you can't get a 1, so you're really stuck if you don't have it. So no values of H. And then 11 through 14, it says find the values of H for which the vectors are linearly dependent. And then this, matrix form. Technically, I'm just checking the whole machine. So zeros out there, I'm just going to put this thing. What about the first one and the last one? So you see, if I divide this one by 2, doing this thing, and we can see it on the line. I'm trying to do 2 basic functions, and this. Maybe what I'll do is I'll stay with this one until we need this. So I'm gonna pull this by 2, that one by 2. And this is going to be 0, 0, 0. So I have a free variable here. And what values of age? Let's see what. Okay. So it does not make any difference what value h has. You're going to have a free variable x3, and it's always going to be dependent. How's that work? No restriction. If we have an age will appear down here, then we'd have this. Have to have a value of age that we want to value 0 for the interim. This is 2. 4 part of that, -3. That makes that a plus 15. Rolling calculations correctly. think what I'm gonna do, I'm gonna divide this one by 2 so we can get one. Multiply this row by -23. And the question is, find the values of h for which the vectors are linearly dependent. So that would mean a linear dependency. This would have to be a 0 row. So then the h, because I want to have my x3 be a free variable. So h equals 26. If it's equal to 26, then it's linearly dependent. If it's equal to anything other than 26, it's linearly independent. Let's say the system of equations. Any questions? Pretty straightforward stuff. Determined by inspection whether the vectors are linearly independent. 16. Okay, my number of entries created and the number of vectors on a good there.
So 3 in the second column.
This is a -3 here. Now, those are multiples of each other, are they? Say that.
Is it row 1 multiple of row 2?
Well, yeah. And I was just looking at the vectors. They aren't multiples of each other. But then if we put it in matrix form, and like you say, if this one can turn out to be multiple of it, but this one's. And I have 2 columns, and I'll have 2 rows that are linearly independent. The first and the last are dependent, but the whole system is going to be independent. it's linearly independent.
Why?
Because if I try to, see, it's 2 columns, 3 rows. So, if I try to get this thing reduced down, I would multiply. Let's see, this one by what? Is 0. E has that. 4. This is a negative. 4. So that would be 5. And then if I multiply that times that, that'd be 1/2. So I go 0, 0. But I have turning points here. So I'm good.
You're multiplying by 3/2.
Did I do something wrong?
I was about to say 6 times 3/2 is 9. So the second
one
row
is-
would be 0s too.
Okay.
And vectors are
All right. In that case, then I have 2. See, actually, this thing, when you multiply it out, you only have x1, x2, because you only have 2 columns. All you need is 2 of those 3 to be independent, but again, the multiply columns. There's only 1, and the others have, there's a 3 variable x2. So these are not independent. They're linearly independent. Which one is this? This is 16. Now, 18 would be by theorem 8. It's linearly dependent because the number of if you put those vectors in matrix form, it's 4, 4, minus 1, 3, 2, 5, 8. Now, in order to get this as AX equals some B or 0 or whatever it is, this has to have x1, x2, x3, x4. And that means that the number of columns is more than the number of values in each vector, or the number of rows. And so you're going to have at least 2 free variables. So it has to be linearly dependent. And that's and then 8. That's what we do for 8. Now, 20 you have a 0 vector, and that one, theorem 9 says if a set of vectors contains 0 vectors, then the set is linearly dependent. But, kind of the reason that it's going to be that way is because when you do your AX, you aren't going to be able to get this diagonals of one alternative because this has to be x1, x2, x3. You can't. You would never be able to get a diagonal for turn points on every row. So that's the reason theorem 9 says that you can't have a zero vector. 22 is just some statements. It says two vectors are linearly dependent if and only if they lie on a line through the origin. So is that true? And it's true if you look at figure 1 on page 59. Notice that line to the origin, they're dependent if they lay on that same line. The figure is showing you that the top one, that they're laying one on top of the other. And that's dependency. By definition of, they're just multiples of themselves. They don't get just a multiple of the other. Okay, B, it says if a set contains fewer vectors than there are entries in the vectors, the set is linearly independent. So that means the values that appear E is less than the entries of the course. Now, is it linearly independent? And that you have to look at the warning on theorem 8. If this be the number of towers is greater than that, then it's linearly equal. But they're saying, does that mean that if this is true, that they're independent? Well, this is not true. And the warning says right there at the bottom, it says theorem 8 says nothing about the case in which the number of vectors in the set does not exceed the number of entries. So if this is always true, when you're deep, because you wouldn't have enough independent equations. But in the other case, it's not independent when this exceeds that, because it can be dependent on two independent. So be careful about making a counter conclusion about a theorem. If it said if and only if, then you would have that statement would be true. And then it says, X and Y are linearly independent, and if Z is in the span of XY, then XYZ is linearly dependent. And that's true, and that's at figure 1 on 59. And then the D part, it says if the set Rn is linearly dependent, then the set contains more vectors than there are entries in each vector. And that's false because that's only one case. At theorem 8, you can have a set of linearly dependent equations if you have zeros in. See, that statement was trying to say this is what always has to happen. What it means is you can have an A matrix where you have zeros in rows, which indicates that you have free variables. So. Is it time for the quiz?
5 minutes.
What?
5 minutes.
That's about it. That's enough quiz.
True.
What?
True.